Okay. Well, thanks very much for the invitation. I tend to speak a bit fast, and so if don't hesitate to interrupt if you want to, I don't know, ask questions or whatever. I'm happy. So you can just unmute and ask a question. For me, it's fine. So I'm going to present some work I've done with a PhD student of mine, Dan Moss, in Oxford, on the use of cut posteriors, which I'm going to describe for semi-parametric inference. I think they can be more widely used in this context than actually they are. And I'll explain why. And I'll be concentrating in particular to the context of semi-parametric hidden Markov models with finite state space. So I'll describe the context of semi-parametric inference and the kind of properties we are interested in, and why we might want to use cut posteriors in this context. And then I'll concentrate on the semi-parametric hidden Markov models and the results we have obtained in this context. So semi-parametric inference, so just notations really. So you have some data, Y, and I index them by N because I'll be looking at asymptotic properties. So N can be seen as a sample size. And some semi-parametric model. So you have theta, which might be the parameter of interest and which is going to be finite dimensional, and eta, which will be the Newton's parameter or not. It can also be a parameter of interest, and it's infinite dimensional, typically functions. And we're going to consider a Bayesian approach. So we put a prior on theta and eta. So pi is a prior. And from that, you can derive the posterior. So we're assuming that there is this dominated model. So the posterior distribution on theta and eta is proportional to the likelihood here times the prior. And the aim of the game here is to make inference. And we want to make inference which is good in theta. So that's the semi-parametric problem. But we also want to allow to be also good in the eta. So both theta and eta can be parameter of interest or also functionals of theta and eta, some functionals. And so there are lots of semi-parametric models that are super well known in the literature. The Cox models by Cox is the most famous one. You can do mean estimation when you don't want to specify the distributions, partial linear models, blah, blah, blah. And the semi-parametric hidden Markov models is one of them. So what do I mean by good inference? Well, in particular for the parametric parts, when it's possible, what we would like to have is sort of optimal properties, optimal and well-calibrated properties, in the sense that sort of one of the goals would be to get what's called the Bernstein-von Mises theorem for theta, which is the finite dimensional part, which says that the posterior distribution of theta recentered at some value, theta hat, and rescaled by square root of n or something going to infinity, goes asymptotically to a normal with mean 0 and variance v naught under when the data come from some distribution p naught. Okay, but more importantly, you also want to have the sort of frequencies counterpart of that, which says that the frequencies distribution of this centering point, so I'm using the same centering point here, centered at theta naught, so which is the true parameter, also converges to a normal 0 v naught. And because you have this duality, so the same behavior for the posterior and the frequency distribution of the centering point, credible regions, so measures of uncertainty in the Bayesian world, will also be frequentist confidence region asymptotically. And so there will be a robustness with respect to the choice of the prior. And also, not only will you have confidence in the point estimators, but you also have like some sort of confidence in the measures of uncertainty. And when I mean confidence, it's a robustness with respect to the prior. Somehow you know that you have made choices in your prior. In high dimensions, choices are not fully neutral in a sense that they don't disappear asymptotically. And here they sort of, to first order, they disappear asymptotically for the parameter theta. And that's reassuring because if you're not too sure about your prior, then you know that the data is going to take over in a sense when you have enough data. And typically, when the model behaves well, V naught minus 1 is a Fisher information matrix, or the efficient Fisher information matrix, which means that not only are you well calibrated, in other words, critical regions are confidence regions, but also the size of the region is optimal. So that's sort of the kind of results that we're looking for. The problem is that typically, so getting semi-parametric Bernstein-von Mises theorems is complicated. It's not easy. There are now some general theories that are around, but they have been applied to only a very specific type of context and limited in terms of the choice of the priors because they are difficult mostly. And what comes out of these results is that often in order to well estimate theta, you need to undersmooth eta, which means that the prior on eta needs often to be not so well behaved for eta, but it's targeted so that theta the posterior on theta is well behaved. And so in other words, often in order to be good in theta, you're not too good in eta. And so you cannot be good in theta and eta jointly with a given prior. I'm not saying that it's impossible. I'm just saying that it's very hard to achieve being both good in theta and eta simultaneously. And when I said good in eta, it means, for instance, that you can estimate it at a rate, which is what you would expect to be the good rate for the given problem, for instance. And it will be particularly true for the semi-parametric hidden Markov models, you will see. And so in this case, what you can do is use the idea of cut posteriors. So cut posteriors have been around in the literature for a while. We're not inventing them. We're just using them in a different context. So what they were originally, so it's a graph I took from a paper by Jeff Nichols and Chris Carmona. It's cut posterior. They were devised when you had different modules associated to different data sets. And somehow you wanted to cut the information going from one module to the other because you don't necessarily trust everything. For instance, if you have two different modules, so here you have two different modules, assume that, whoops, I don't know what I did. Yeah, my God. It's here. No, it's not there. It's here. Yeah. So here you have some data Z and some data Y, and you have a model that says that Z depends on some parameter phi, and a model that says that the data Y depends on both phi and theta. And imagine that you're not quite clear about whether this model is well specified. Maybe it's you've put a model, but you're not quite clear about it. If you do joint inference, so you do by a full Bayesian inference, the inference that you will have on theta, on Y, on theta, is might be polluted by the model that you have there. And if it's misspecified, globally your model will be misspecified and you might misestimate theta. So that was one of the reasons why people use cut posteriors. They're also called modularized posteriors in the literature, but it's been around for a while. And another reasons might be for computational easiness and things like that. There are like really interesting paper by Liu, Berger, and Bayari in 2009, and a recent paper by Jacobs and Pierre Jacob and some co-authors, and Chris Carmona and Nichols on that. But so that was the context where they used cut posteriors. So here in our context, it's going to be a bit different because we are going to have just the same data set, but we're going to use two different priors in a sense. So you have a prior pi1, that's a prior on the full parameters, theta and eta, but it's targeted so that you know that the posterior on theta is well behaved. So for instance, the posterior on theta satisfies Bernstein-von Mises theorem. So you can recover, so you compute the full posterior distribution on theta and eta, you marginalize out, so you integrate out eta, and you recover the marginal posterior distribution on theta given Y. And the pi1 has been chosen so that you know it's well behaved. Now, but because it's been chosen like that, it's not necessarily well behaved for eta. So what you're going to do is, now that you have that, you're going to consider a second prior, which is targeting towards eta. For instance, if eta is a function, a density, you might put the shape process mixtures on that, or something like that, whatever your favorite prior you like on eta. And which potentially depends on theta. So you can look at it as a conditional distribution on eta given theta. And then from that, you can recover the conditional posterior distribution associated to pi2 on eta given theta and yn, which is the likelihood times the prior. And now if you combine the two, you have a proper probability distribution on theta and eta, but it's not a proper posterior distribution. That's the product of this marginal pi1 of theta given y times the product of the conditional distribution on eta given theta and yn. And because they come from two different priors, pi1 and pi2, they do not necessarily form a joint posterior. You might end up by having a proper posterior, but it's typically not going to be the case. Okay, and so in particular, if you had chosen pi2 to be equal to pi1, then you would get the proper posterior. But you allow yourself to choose a different pi2 for eta at a bit like at a second stage if you want, and then you have this is a real posterior, a real distribution on the parameters. It's a real probability on the parameters, but it's not a full posterior. And that's going to be the object that we're going to study and that we're going to use to be able to estimate everything we want, or almost, in these semi-parametric hidden Markov models. So what kind of properties are we going to look at? So we're going to look at Bernstein-von Mises properties, which I have described already. But for the non-parametric part, you might want to study sort of the first type of result that you might want to have are contraction rates, which give you some notions of rates of estimation. So it's a bit like pointwise rates of estimations, typically these contraction rates. And so what are contraction rates? A contraction rate is defined as a sequence epsilon n that goes to 0, such that the posterior probability of balls with respect to some metric d around theta naught, which is a true value of the parameter, at the radius epsilon n, this posterior probability goes to 1, or the posterior probability of the complement, which is written here. So the posterior probability of not being close to v naught at the rate epsilon n goes to 0 under p theta naught as n goes to infinity. So what it says is that the posterior distribution shrinks towards the true value. So you're going to learn, ultimately you're going to learn the true value. And the rate at which it shrinks is epsilon n. And so when you have a posterior contraction rates, and if you derive an estimator from the posterior distribution, then this estimator typically is going to converge to theta naught or v naught at the rate epsilon n, at least as far as d is concerned, using the same metric. Okay. And so there is any questions so far? It's fine. Okay, good. So there is there is now a very nice theory that has been developed by Gozal and van der Waart in the early 2000s to devise some tools, generic tools to obtain these posterior contraction rates. And so these tools are the following. So I'm just going to give it right away. So essentially what you need to check is two types of condition. One, which is called the Kullback-Leibler conditions. Essentially, it says that the prior mass of Kullback-Leibler neighborhoods of your truth is large enough. And so there is the epsilon n is given there. So somehow you look at Kullback-Leibler neighborhood of size epsilon n squared because it's Kullback. And they need to have exponential, at least exponentially small prior mass. And the second type of conditions is the testing conditions. And that's sort of what sort of drives D. So that's the only condition that depends on D. And I'm not going to spend much time there because we're not going to talk too much about that here. But so essentially what it says is that there is a waylaid theory for real posterior. So if you have a true posterior, then you can use the Gozal and van der Waart theory and you can apply it and then you get the rates. And it's been done in many models. And so you can use these models. The problem is that in our context, we're not going to use posterior distribution, but cut posterior distribution. And so what we need to do is adapt the theory to the cut posteriors. So the good news, and it's really not a huge effort, the good news is actually it's easy to adapt. And essentially you can get the same result with cut posteriors under the same sort of assumptions. So whatever has been found before for real posterior can be applied directly to these cut posteriors. So it's a good news because you don't have to reinvert the powder again. It's a French expression. So typically, so what are the assumptions? How I'm going to write that up like that. So what it says is, so what you have to prove with cut posteriors is that the pi1 is well behaved. So here I've said you have a Bernstein-von Mises, but you don't have to have a Bernstein-von Mises. It can be more general, but because this is what we're going to have in our context, so that's what I have written. So if you have a well-behaved marginal pi1 distribution, then what you need is a Kullback-Leibler condition, which is essentially the same as what was before, and a testing condition, which is exactly the same as before. So as soon as you have a well-behaved pi1, then you just have to use the same theory from Gosal and van der Waart, and you get your cut posterior contraction rates. So the P tilde is a cut posterior. Okay, so now what I'm going to do is to study these sort of tools in the context of the hidden Markov models. So essentially,
can I ask a quick question? I was just a bit lost on the notation on the previous slide. So the pi1s are these posteriors, but in the KL, the P's, Pn, what exactly were they?
So these are the true distributions, and V var theta naught is the true parameter. So the whole parameter is theta and eta.
Okay.
So this is a true distribution, and this is the distribution in the model.
Right. Okay. Thank you.
Yeah. So because we don't necessarily have RID, so it's the distribution density of the distribution of the n sample on the n observations. So this is why you have n here as well. So if you had RID observations, the KL of Pn and P theta naught n is the sum, is n times the KL of each one for each observations. Is that clear? Thank you. Okay, so
could I ask also a question, please?
Sure. Yeah.
I had a question about what you said at the very beginning about how eta, one of the issues is that you need to have a prior which is under smooth. Is that what you said?
Yeah.
Could you have intuition why that's the case? And
so this is something that has been observed in examples. So for instance, we had a paper on semi-parametric Bernstein-von Mises when you wanted to, so you have a model on densities and you want to estimate the conditional distribution, cumulative distribution function, so CDF, at a given point. So there is the empirical distribution estimator, which is super well behaved. And it turns out that if your prior on the density is reasonable, like for instance, reasonable, like in particular, if you tend to have an adaptive prior, you take a histogram and you put a random number of beans, or if you take mixture models with a number of components, you might run into trouble because they might be too smooth in a sense that a CDF, it's an integral of a function times the density. And if your model tends to be too smooth for the density, the integral of the function times the density is going to be biased. It's a bit like misspecification. Somehow, if your model for the density tends to estimate a function that's smoother than your truth, then you will have trouble estimating this parameter theta. And so if you tend to be conservative in the sense that your function is under smooth, you will allow for much more or many more function of interest that you will be able to estimate correctly. Does it answer the question?
Yes, yeah, thank you.
And in this context, well, for instance, for mixtures of normals for density estimation, we have no results in the literature. I mean, because they are difficult objects, and proving Bernstein-von Mises is very complicated. And so we only have proofs of Bernstein-von Mises for well-behaved priors, like expansion on the basis, or that's typically expansion on the basis, and that's it essentially, or polyatries. And but there exists now in the literature quite a lot of counterexamples where they don't hold. And typically they don't hold because somehow your prior tends to have not enough coefficients that are taken into account that are used to model your density in a sense, or your function.
Okay, great. Thanks.
So now, so what we're going to do is consider a semi-parametric hidden Markov model. So what do I mean by that? It's so you observe the y's, and so it's a hidden Markov model. So it's a hidden model in a sense. So yt given some latent states xt equals j follows some distribution fj, and it's finite state space, which means that the states, hidden states, belongs to 1 to k. And in this talk, k is known, but possibly we can extend that. And it's hidden Markov because the xt, so the hidden states, form a Markov chain with transition matrix Q. So Q is a transition matrix of the hidden states, and the fj's are called the emission distributions, so that the conditional distributions of the y given the x. Okay, and so now, so this is non-parametric in a sense because the parameters are Q, the transition matrix, and the emission distribution. So we would like to make no assumptions or hardly any assumptions on the emission distributions. So this is semi-parametric because you have a parameter of interest, a finite dimensional parameter Q, and infinite dimensional parameters, which are the emission distributions, and you have k of them. So usually hidden Markov models are considered in a parametric framework, or they are extensions of mixture models. So they are considered in a parametric frameworks where the emission distributions belong to a parametric family, and the normal one is like one of the most famous ones. But the problem is that they are strongly dependent on this parametric family, and if you're misspecified in the parametric family, you can be quite badly behaved in terms of what you want to do. Of course, it depends on what you want to do, but for instance, if you want to do clustering or segmentation in the case of hidden Markov models, then the segmentation procedure is going to be strongly influenced by the choice of the model that you put on the emission distributions. And it's been like there are lots of people trying to do robust segmentation. And of course, what does it mean to be robust segmentations? It's often, I hope I'm not going to offend anybody, but it's always something that sort of gets a bit on my nerves when people say we want to do robust segmentation. So they start with a parametric model and they say, but it's not good enough because we want to make it robust. And then they don't define what it means to make a segmentation if it's not within a model. The segmentation makes sense here because you know exactly what a component is. If you don't define what a component is, then it makes no sense to say it's well-behaved or not well-behaved, in a sense. So what's the difficulty in such context, and it's a real difficulty, is can we just get rid of this parametric assumption, or can we relax the parametric assumption to some extent, but still be able to give a meaning to what a component is? Because otherwise, what does it mean to make clustering? Or, I mean, it means a lot of things to make clustering, but how can we validate the clustering in a sense? What are the criteria that we can use to validate the clustering? So there has been quite a lot of work to relax these assumptions. In mixture model, for instance, people have tried to use the log linear, log concave densities and things like that, symmetric densities. But even if you force your density to be symmetric, it's still not fully identifiable and things like that. So unless you make no assumption, unless you make specific assumptions, things are not identifiable, and then the clusters are not identifiable, for instance. But there is a magic in the case of mixture of Markov models, which is that as soon as a latent variable xt is Markovian or actually dependent, then you can make inference and everything is identifiable. And we started realizing that in a paper by Elizabeth some years ago, so it's been a while now, in the specific case of location hidden Markov models. So yt equals mj when xt equals j plus some noise epsilon t. And epsilon t doesn't have, you don't want to specify the distribution of epsilon t. So it's unknown. And so that the xt are Markovian, and what you observe are the yt's. So what identifiability in this sense means that if you're looking at consecutive observations of yt, so y1, y2, y3, and you look at the distribution of y1, y2, y3, or y1, y2, which is g here, then if g qf equal prime and f to be equals to your f prime. and m equal to m prime, because there is also the parameter m. And what's magic here is that if determinant of Q is positive, so if you have ID observation, the determinant of Q is not positive, so mixture models don't work. But if the determinant of Q is positive, for instance, in the case of many Markov chains cases, then you have identifiability, like in the sense that GQM equals GQ prime M prime and F, I forgot to say F, implies that Q equals Q prime, M equals M prime, and F equals F prime, and even K equals K prime. But yeah. And that's for a specific model. And then later on, Elizabeth, Garcia, and some co-authors proved that it's more general than that. If you have a general hidden Markov model, as I wrote before, so XT is finite state space. It's a Markov chain with matrix Q, transition matrix Q. YT given XT follows the distribution Fj if XT equals J. Then if you look at the distribution of 3 consecutive observations, which I call G3 here, QF, then GQF equals GQ prime F primes implies Q equals Q prime and F equals F prime and K equals K prime. As soon as one of the determinant of Q or determinant of Q prime is positive. So as soon as you have dependence, then you can identify everything. And it's a bit of a miracle in a sense, because now you can do segmentation in a robust manner without to specify the parametric models for the emission distributions. So that was some years ago. And because you can do that, then you can start to consider non-parametric procedures. So you could deploy on Q and on F and try to estimate everything. And we had a PhD student called Elodie Vernet at the time, like 6 years ago. And she derived some theory there. So following Gozal and van der Waals technique, in a sense, where she gave general conditions on the prior and on the true model to obtain posterior contraction rates for the G functions, which are the density of the observation, so the marginal densities of the observations. So these posterior contraction rates, I mean, it was already quite a work, but they don't give us some results on the parameters themselves. So we don't get the Q, contraction on the Qs, and we don't have some results on the estimation of the emission distributions. What it tells us about is if you wanted to do prediction, for instance, then you could do prediction because you have a contraction on the distribution on the Ys, the observations, marginal distributions of the Ys. And going from G to Q and F is not a trivial matter. It's difficult. So in the same time, in the frequentist literature, there existed some completely different results based on spectral methods where people could estimate the Q transition matrix at the rate 1 over square root of n. So asymptotic normality was not proved, efficiency nothing was proved there, but at least you could estimate Q at the rate 1 over square root of n, and later on Garcia and other co-authors proved some estimation of G at the rate epsilon n as well. In parallel, because related to this sort of identifiability issue result, there is also an identifiability result for the case of mixture model, but when the observations are at least of dimension 3 and Y given X, so distribution of Y given X is made of 3 independent distributions. In other words, like if Y is Y1, Y2, Y3, the distribution of Y given X is F1 times F2 times F3. So it's a product of 3 independent distributions. So they are conditionally independent. And so when you have this structure, then you can identify everything. And somehow it's because you have this structure that it works also for hidden Markov models. And then in this context, we were able to use the Bayesian method with a very simple prior, which I'm going to sort of reuse for the hidden Markov model, to prove that you can construct estimators that are frequencies that are square root of n convergent with asymptotic normality. And the prior associated is actually also satisfies the Bernstein-von Mises. But that was for the mixture model, which are much easier models. And so the aim of the game when we started was to extend these results to hidden Markov models. And then also to get some results on the non-parametric part, which are the emission distributions and some other functionals of interest. So let's go back to our hidden Markov models. So recall that you observe y, yt given xt equals j follows fj, which is a known, and the transition matrix, which is the probability of xt given xt minus 1, is q and is also unknown, but the number of states are known. So we want to estimate, to construct some prior such that to get estimators of q which converge at the rate 1 over square root of n. You want potentially to have a asymptotic normality of the marginal of the distribution, the Bayesian, the posterior distribution, but also a Bernstein-von Mises result. So this sort of duality between the frequencies and the Bayesian, so that credible regions are confidence regions. And potentially also you want to be efficient. So you want to prove that your estimator is the best you could obtain asymptotically to estimate Q. So that's for Q. But as I said, we might also want to estimate the emission distribution. For instance, if you want to do smoothing, so if you want to recover the states given the data, then you need to estimate the probability of xt equals j given all the data, which are the smoothing probabilities, and they are functionals of Q and the emission distributions. And so, we want to estimate correctly the emission distributions as well. And to do that, we're going to use the cut posterior, and we also have to invent some, or to obtain an inversion inequality that goes from the G densities, which are the densities of the Y's, to the densities of the Y given X. So now I'm going to describe how I can construct a prior pi1, which is going to be my first prior in a sense, that will lead me to a very good estimation procedure for estimating Q. And it's going to be a very basic and stupid prior. What I'm going to do is I'm going to consider random histograms for modeling the densities, the emission densities. And so histograms can behave well if you have a lot of bins, but here I'm not even asking a lot of bins. I have a fixed number of bins, and I'm going to assume that to model my densities as piecewise constants. So they are random histograms with a fixed number of bins. So you can't have, I've written everything in 0, 1. Obviously, it doesn't have to be in 0, 1. It can be for one thing, it can be multivariate. And also, but you still have to be in the space. So you have to have a finite number of bins. But the partition needs to have one specific properties, which we call admissibility. So in the sense that this matrix has full rank. So what is this matrix? In each row corresponds to a different emission distribution. So I have k components, so I have k rows, k emission distributions, and each column corresponds to a different bin. So that's this in row 1, I have f star of bin 1, f star of bin 2, f star of bin L, and in row k I have the same with f star k. So and f star is the true distributions. So for the true distributions, I need to make sure that this matrix has full rank. So if you have a well-behaved, or if you have well-separated, so if your emission distributions are linearly independent, you can find partitions of size at least k that are such that the matrix is full rank. And if you increase the number of bins, then you increase the chance of getting full ranks somehow. So getting full ranks is not going to be something super difficult, but you need to make sure that you have full ranks. So of course, it's always an assumption that you're making when you're making inference. There's always a risk that it's not full rank. And so you have to be careful there in practice. So you have your finite number of bins and it's fixed. You model your density by piecewise constant functions. So you can't be more simple than that. And the PCs, they are normalized, auto-normalized in a sense. So the sum of the WJs are equals to 1. So this is they belong to a simplex. So typically, for instance, you can assume that the WJ for each row, WJ are going to be Dirichlet distributions, and Q follow some distribution on transition matrix. For instance, each row is also a dirichlet distribution. So you have a very simple model. And if you put dirichlet distributions, then the inference is going to be conjugate. And so the implementation of the posterior distribution is going to be super fast. But more surprisingly, actually, with this very simple basic prior, you can prove that for estimating Q, it's well behaved, and it's very well behaved because you have a Bernstein-von Mises result which says that the posterior distribution associated to this prior for a fixed partition with a fixed number of bins as soon as it's admissible, centered at the MLE in this model, because I'm assuming that it's a model. That's my model that I'm assuming, but I'm not assuming that the true belongs to the model. I'm not assuming my true emission distribution are piecewise constant. I'm using this model as a toy model to make inference without thinking that it's a correct model. Okay, but it doesn't matter as long as so I have an MLE in this model, and what it says is that the posterior distribution is going to be asymptotically normal, centered at the MLE with variance, the inverse of the Fisher information matrix in the model divided by n. So it's a typical Bernstein-von Mises result. And it's Bernstein-von Mises because I also proved that the MLE is also asymptotically normal with mean 0 and with mean Q star and variance, the same variance. And so credible regions are going to be confidence regions. So it's a good thing. And my Bayesian estimators are going to converge at the rate 1/√n. So why does it work? Why? I mean, it's a bit of a miracle because it's such a stupid model that you'd think it would never work. The reason why it works is because these piecewise constant functions for the densities doesn't make your model misspecified. What it does is that it sort of reduces the information in your data into yi, which you're transforming into indicatrix that yi belongs to L. And so it's like transforming ID data from F into multinomials, in a sense. So at the end of the day, you're playing with a model which is a hidden Markov model of multinomial emission distributions. But it's a well-specified model of multinomial hidden Markov models. And so if I wanted to do something to estimate my emission densities, or if I wanted to estimate functionals of the emission densities, I wouldn't be very good because I have transformed the density by just the mass of the beam, so it's not precise enough. But because I want to estimate Q, this is not disturbed by the fact that I have a multinomial. Q is still the same, and so I'm very good for estimating Q. And I have transformed a non-parametric model into a parametric model, and I have all the theory for parametric inference in hidden Markov models, which goes through. And so it's not difficult. So even like proving the Bernstein-von Mises result is not so difficult in this case, although it starts with something which looks like difficult. The problem is that the variance that we obtain, I mean, at least we have square-root-n convergence rates, but we're not sure that the variance is optimal. And obviously the variance depends on the partition, and the variance depends on the size of the partition and things like that. And so can we select the partition optimally in a sense? What would be like the optimal partition? How do we have to let L be super large? Or does it help to increase L? All these questions are not answered. And so what we're going to prove now is that if you let L go to infinity slowly, then you are going to construct estimators that are efficient. So what does it mean to be efficient in a semi-parametric context? It means that the asymptotic variance is the best you can obtain. So you can't find estimators that are regular that will have a variance which is better than the one you have. So that's essentially they are the best possible estimators for the semi-parametric problem. And that was somehow the sort of a difficult part in this for the semi-parametric inference, which was to prove that the efficiency. And so what you want to prove the efficiency, what you have to prove is you have to prove that the space of cores associated to the model with the partition L, when you let L go to infinity, so you take partitions that are finer and finer, then this core set, which is a set of functions, converges to the score set associated to the whole semi-parametric non-parametric problem when you make no assumptions of the emission distributions. And so that can be done. So the scores, so the reason why it was difficult is because the scores for which corresponds to the derivative of the log likelihood associated to the densities in a sense, so the emission densities, they are not so nice. I mean, that's the form of a score. So they don't look too good. And the score associated to Q, they are the derivative with respect to Q, and they are easy. I mean, they look a bit like that, but they are not so bad. And so proving that the set of such scores corresponds to the set of the same scores, but when L equals infinity, was not obvious, but that can be done. And once you have proved that, then the Fisher information matrix in model L, you can prove that the Fisher information matrix in model L converges to the efficient Fisher information matrix, and the maximum likelihood estimator is asymptotically efficient, and the BVM is an efficient BVM in the sense that the posterior distribution has the right variance as well. So you have not only obtained reliable confidence regions by using credible regions, but also the size is optimal. So that's all good in a sense, but it's only for Q. And if you remember, the prior I have put is totally stupid for the emission densities, because I'm sort of assuming that they are piecewise constant, and the number of pieces is like not very large. So it's not at all a good model for the emission densities. So there is no chance I can recover a good model for the posterior in the posterior distribution for the emission densities. So this is why I'm going to use a cut posterior, because I want not only to be good for Q, but I also want to be good for F, for the emission densities. So before I can be good for F, I will need to prove that I'll be good for G, which is the distributions of the observations, so the marginal distributions of the observations. In particular, if I look at 3 consecutive observations, then the marginal density of 3 consecutive observations has this form. So it's a function of the Q's and the F. And to prove that I can estimate well F, knowing that I'm estimating well Q, I will have to prove first that I can well estimate G. So to do that, I'm going to use a cut posterior. So I'm going to now use my pi1 I have just told you about, with a number of beams that large but not too large. From that, I recover the marginal posterior distribution of pi1 of Q given the data. I store it on the side in my computer. And I'm going to condition on Q now. For each Q, I'm going to look at the conditional distribution of F given Q and Y by constructing a different prior for the F. So I'm sort of forgetting what I did before, and I will imagine a new prior for F. So if, for instance, I can use Dirichlet process mixture of normals, I can use polyatries, I can use log Gaussian processes, whatever your favorite prior is. And my full posterior, my cut posterior, is going to be the product of the pi1 I had just told you about, with this conditional distribution on F given Q and Y, based on this new prior. Okay. And hopefully, by doing that, I get the best of both worlds, in the sense that I know I'm good for Q, and hopefully I can also be good for F by this with this object. So one of my favorite priors in my case are Dirichlet process mixtures. So here I've written them as location Dirichlet process mixture of normals, but they can be location scale if you're careful about the scale. You can use polyatries or random histograms, but this time you put a prior on the number of beams. So you can also put a prior on where the cut of the beams. You can use also splines or log splines or whatever. This part, it's not so important. I mean, it is important in practice, but you can choose the one you prefer. And so now we want to understand the behavior of this new posterior, which is a product of this marginal posterior on Q times the conditional posterior on F given Q. So I use the result I had given before, that the fact that the only thing I have to do is make sure that pi1 is well behaved, and I know that. And then I just apply the theory of Gaussian and van der Waals, because they are the same techniques, and to study the behavior of the cut posterior. And for that, the problem is that I can use the result of Elodie-Vernet, which gives me some contraction rates on the G functions, on the densities of the observations, and not on the densities of the observations given the states, which are the conditional density, the emission densities. But that's my first result. So the first result is to apply Elodie-Vernes calculations, put everything I have done so far together to prove that I have a contraction rates for the distribution of 3 consecutive observations, G, which have this form, remember. So it's a function of Q and F. And if I use Dirichlet process mixture of normals, and if my emission densities are Hölder, for instance, then I recover sort of the usual rate for Hölder density estimation, which is n to the power minus beta over 2 beta plus 1 in dimension 1, or 2 beta plus d in dimension d, up to a log n term. If I used random histograms or splines, random histograms, then I'm forcing beta to be less than 1, and I have the same rate for beta less than 1 because they are piecewise constant functions. Polyatries is the same. And these priors, for instance, are adaptive. They are adaptive in the sense that I don't know beta, so my prior doesn't depend on beta. I'm putting, for instance, if I use a Dirichlet process mixture of normals and I put a inverse gamma prior on sigma, the scale for the location mixtures, then I have an adaptive posterior contraction rate because the rate is sort of the best I could obtain for Hölder beta, and that's exactly what I get. And the reason why it's interesting is that often Bernstein-von Mises results are hard to obtain with adaptive priors. And the reason is because for obtaining Bernstein-von Mises results, you need to undersmooth. And adaptation doesn't undersmooth. It typically tends to a bit oversmooth, or at least obtain the smoothness. So you're not undersmoothing, and so that's a bit incompatible with obtaining Bernstein-von Mises results. But here, because I'm using the cut posterior, I'm securing Bernstein-von Mises result on Q with something totally undersmoothed because it's piecewise constant with a fixed number of bits. And then I'm using a non-adaptive prior for the S. But then it's only half of the story because I have the G, but I don't have the emission densities. And to be able to go from G to F, you need to have an inversion inequality, which is something we obtain in L1. So posterior contraction rates are typically obtained in L1. And so that's what you get. You obtain your inversion inequality, and so you get the epsilon n rate I obtained there will lead to an epsilon rate for the emission densities. It's also good. So for instance, in the case of mixture of normals, I have n to the power minus beta over 2 beta plus 1, and that's what I expect. So that's good. You can also work a little harder and get contraction rates for smoothing. So what does it mean, contraction rate for smoothing? Of course, what you want to do is segmentation, but the segment is a random object, and so you cannot, with probability going to 1, recover a random object. So, the best you can try to obtain is estimate the correct smoothing probability. So, which is p star of x equals 1 given x equals j given the data, and so. There was a paper, a very nice paper by Garcia and some co-authors that had some kind of inversion inequality, which says that if you're good in Q and if you're good pointwise in F, then you are good also for the smoothing. The problem is we are not good pointwise, but we are good in L1 in F. And so you had to prove that. So in practice, the frequentist people, because they are, unless they either they prove a subnorm result in F, so they have a subnorm contraction rate, or they have to split their data in two, estimate the parameters with part of the data, and estimate the smoothing with the rest of the data, which is not satisfying. But what's funny is that because it's a Bayesian approach, you're integrating out the parameters, and somehow it's another kind of miracle. You can go from this sort of pointwise rate to an L1 rate in probability. And you can prove that you can estimate the smoothing with the same rate epsilon n as you can do for the F and for the G's. So yeah, the difficulty with the cut is that it's a little more painful to implement than just a full posterior. And the reason is that, I'm going to write now, that you have to, so you simulate the pi1, that's super simple because it's a basic model. So you recover a bunch of Qs. So you have, after thinning, you have like a sequence of Q from the pi1, from the posterior distribution on pi1. And now for each Q, you need to simulate from the stationary distribution of F given Q11, which means you need to run a mini chain each time for each Q to make sure that the F that you're getting comes from the stationary distribution of Q of F given Q and Y. But because the posterior on Q is so concentrated, because you have a Bernstein-von Mises result, Q doesn't vary much. And so if you initialize using the previous value, you're not going to be too bad. And so actually the mini chains in our case can be very short. And so it's not too time consuming to do the implementation. Anyway, so you run the algorithms and a bit of relaxation. Here are some simulations. So we have a very basic simulation study. We did it on 2 states. Here are the 2 parameters. So you have a normal, I can't remember, I think it's a normal 1, 1 and normal minus 1, 1 or something like that for the emission distribution. So they are well separated. So it's not a difficult case too much. We have run pi1, so piecewise constant functions. We use the dyadic partition based on the quantile of some function, but not associated to the true distributions at all. So here that's Q11 and Q22, or Q22 and Q11, depending on, there is a label switching issue here. It's when we have taken 2 bins. Here we have taken 4 bins. Here we have 8 bins, I think. Or maybe it's 8 and 16, I can't remember. And then we start to have a lot of bins. This is 64 and this is 256. And so what do you see is that with 2 bins, it's well centered, but it's a bit wide, which is a bit what you had in the theory. So apparently the partition is admissible. And now as you increase the number of bins, the variance gets smaller, but then it starts shifting. So like here, for instance, you start to be a bit, so here like there, you start to shift. So the centering points start to be away from the truth. Obviously, usually you don't know the truth, but there is a way around it. And when you start to really increase the number of bins, it becomes like completely crazy. So you really don't want too many bins because then the inference is bad, is very bad. And it's better to be here than there, in a sense. It's conservative, but it's better to be here. But what's nice is that, and the same thing when you have 8,000 observations. What's nice is that somehow you start seeing a shift. And so at least visually you can, it's for the moment we're only at the heuristic level. If you run your pi1 on the various values for the number of bins, and at the beginning they are all centered at the same value, but the variance shrinks. And after some time, when you increase the number of bins, they start shifting. And that's where you know that you have too many bins somehow. And so now these are for pi1, these are the estimates of the density. So 2 bins is terrible, of course. You increase the number of bins, it becomes crazy. And here it's not too bad, but it's not too good either, because you have 500 observations. And of course, it's piecewise constant, so it's not very good for a smooth density. Now and the same with more. And now if you run pi2, so you do the cut posterior story. So I don't think you see very much. I'm sorry about that. I'm going to draw. So this is the truth. And but trust me, so the truth will be somewhere around there. Oops, sorry, so it doesn't look like a question. And that's the quartiles associated to your estimator. So that's F1, F2. And we have made tries where you increase the number of mini chains in the algorithms, and we see that actually, so 10 is enough. So that's a very reassuring thing because it means that you can be quite efficient for the estimation procedure. And also for the smoothing here, so there are plots for the smoothing. So the aim of the game was to estimate the posterior probability of xt equals 1 given the data. And these are the true smoothing probabilities, and delta t is the difference. And here what you have, I don't know if you can see, this is the absolute value of delta t. So here you have 1,000 observations, and that's and I have plotted the delta t. So when with 1,000 observations, it's not too big, but it's not too small either. It's still a bit over the everywhere. And when you increase, you go from 1,000 to 5,000, then it starts shrinking very much towards 0.05. Most of them are around between 0.0 something and 0.05. So it's quite good, and you do see that there is concentration as n goes to infinity. And in particular, you can count the number of times that you are misclassifying using the smoothing as a classifier. And with 1,000, you're misclassifying 5% of the time, and with 5,000, you're misclassifying 6% and 4% of the time. So now conclusion. I'm going to go fast. So the sort of general story is that cut posterior. I'm not saying that we should always use cut posterior for semi-parametric inference. What I'm saying is that if you are interested in various aspects and you know that there might be incompatibility with the or it's very hard to find a prior that makes everybody happy in a sense, the use of cut posteriors can be a way around the difficulty. Because then you can calibrate it so that you're good for one part of the parameter, let's say Q, and you're also good for another part of our parameter, which is F, and for reasonable functionals of the two. In the case of hidden Markov models, I think, well, I don't know. Personally, I find it quite exciting to know that I can do reliable non-parametric inference in models like that. In particular, if I want to do clustering or segmentation, it's quite remarkable that you don't have to make assumptions on the emission distributions, in a sense. It's also quite remarkable that you can get efficient semi-parametric inference in such complex models, because efficiency in hidden Markov model is not trivial, even in parametric cases. Yeah, and that's it. Thank you.